Let's consider a special vector function r of t. R of t is special in this case because I want it to produce vectors that each have a magnitude of 2. If that's the case, then we can kind of think of r of t as a vector that's mapping out a curve that's on the surface of a sphere. The sphere has a radius of 2. We can see that in the image on the screen. R of t is the black vector function that starts at the origin and points to the blue point P. The blue curve that exists on this sphere is all of the points that are generated by R of t. If I wanted to find a tangent vector for that blue curve, I would use dr dt, since the blue curve is generated by R of t. And then I would naturally assume that the tangent vector, which we see in red, is tangent to the blue curve. Now, what's neat about this special function, r of t, is that because it looks like the radius of a sphere, dr dt would have to be tangent to the whole sphere. And when you have something tangent to a sphere, you get to assume that that thing is perpendicular to the radius of your sphere. We know that when two vectors are perpendicular to each other, their dot product is equal to 0. So if we're talking about this special function r of t that generates vectors that are all the same exact length, then we can see that the consequence is the tangent vector is perpendicular to that vector function r of t. Now we've concluded that visually, but we could also do this using derivations. So if we started off by saying that the dot product between r and itself is equal to a constant, which would be true for this special vector function that we're talking about here, but it doesn't have to be any particular constant, as long as there is no t values there left in the dot product. If r dotted with itself produces a constant, then we can take the derivative of both sides of that equation. On the left, we're taking the derivative of a dot product. On the right, we're taking the derivative of a constant, and that's a scalar constant. The derivative of any constant is 0. We learned that back in Calc 1. To take the derivative on the left-hand side, we need to use the derivative rule for the dot product. Applying that dot product rule, we have r prime dotted with r plus r dotted with r prime. And we still have that that's equal to 0. Now we know that the dot product is commutative. So r prime dot r and r dot r prime, those are going to calculate the same value, which means we can combine them and call it 2 times r dot r prime. And we could have used r prime dot r, but I picked this one. The factor of 2 out front can be divided off, and so we're left with the consequence that r, the original vector function, dotted with r prime, the derivative of that r function, is equal to 0, meaning that the vector function is perpendicular to its derivative. Let's do an example of calculating a derivative of a dot product or a cross product, for example. We have two vector functions on the screen, the vector function r and the vector function u, and we want to calculate the derivative of the dot product between r and u. Now we could dot r and u together and then take the derivative of the scalar that comes out of the dot product, or we can use the dot product rule, which is what I want to demonstrate. So we're going to do it that way. That rule tells us that we need to take the derivative of r, and then we're going to dot that result with u. And then we need to take the vector function r and dot that with the derivative of the vector function u. So we need to calculate a couple of derivatives. Let's go ahead and do that on the side over here. Taking the derivative of the vector function r, we know we can do that piece by piece. Actually, let's just write this up here. R prime would look like 6I hat. J prime would look like 8t plus 2. And then for the k component, I would have 5. So we have r prime. We also need u prime. For the I hat component, I'd get 2t. For the j hat component, I would have 2. And for the k hat component, I would have 3t squared minus 3. And we want to plug those into our product rule expression that we have. So we need r prime here, and we need u prime here. So then that would look like 6I hat plus 8t And now we can evaluate our dot products. Maybe we want to go in and replace u and r with their definitions. That's up to you. I'm going to read it as this vector dotted with u, and I'm just going to pull the values of u from over here. So 6I times the I component from u, that's going to look like 6 times t squared minus 3. And when we do dot products, we are taking two vectors and turning them into scalars, so there's no I hat there. Then I have the j component, 8t plus 2, times the j component from u, which is 2t plus 4. Then the k component, that would be 5 times the k component from u, t cubed minus 3t. That's our first dot product. Then we need to do the dot product between r and u prime. So the I component from r is 6t plus 8 times the I component of u prime, which is 2t. Moving on to the j component, the k component. And now we just need to simplify and combine like terms. Now that we've distributed everything, we need to go through and combine like terms. I'm going to do this by trying to pick out terms with the same degree. So I have a t cubed here, and I have a t cubed here. Combining those together, we have 20t cubed. Next, I'll look for the squared terms. I have a 6, a 16, a 12, and an 8. They're positive, so that would give me a positive 42t squared. Next, I'll look for the linear terms in t. Here I have a 32, a 4, a negative 15, a positive 16, a 4, and another negative 15 to get 26t. The only thing that is left is our constants. So I have a negative 18, a positive 8, a negative 6, and that's it. So that leaves me negative 16. So if we wanted to, we could copy that answer up here at the top. 20t cubed plus 42t squared plus 26t minus 6. All right, let's move on to the next one, the derivative of a cross product. And this cross product involves the vector u and the vector u prime. If I were to evaluate the actual cross product, I would have to plug everything into the 3 by 3 determinant, or I can use the product rule for the cross product, which says I would take the derivative of that first vector, and then I would cross it with that second vector. Then I would take my first vector and cross it with the derivative of the second vector. Now we're using two separate notations here, the d dt derivative and the prime. So let's pay attention to that because this guy and this guy, they mean the same thing. If I'm applying the derivative to u of t, that's the exact same thing as u prime of t. So if we transition everything into the same notation, this first term would look exactly like u prime of t. And then I'm crossing that with u prime of t. So transitioning to where we're using the same notation can show us that we're crossing the vector with itself. And then in this next one over here, we have u of t crossed with u double prime of t. Now, we've learned before that a vector crossed with itself actually results in an identity. That identity tells us that any vector crossed with itself is equal to 0. So really, the only thing we have to evaluate is the cross product of u with the vector u double prime. So we do need to go back and calculate u double prime, taking the derivative of each of our component functions. We get the vector 2, 0, 6t, so we can calculate that cross product between u and u double prime. Plugging in the vector u first. Then the vector u double prime. And then evaluating our determinant. Kind of running out of room here, so I'm going to write the k component below this. That'd be 0 times t squared minus 3, and then minus 2 times 2t plus 4. And then we can clean this up. Distributing through our I component, we have 6t times 2t plus 4. That would look like 12t squared plus 24t I hat. And then in the j component, we would have 6t cubed minus 18t, 2t cubed plus 6t. Combining those, we would have, oh, and that's minus all of that. So we need to distribute our sign here. So we would have negative 4t cubed, 12t, j hat. And then for the k component, we need to distribute our negative 2. We would have negative 4t minus